Have you ever wondered how the devices in your home are connected to each other? From the TV you watch, to the lights you turn on, and to the air conditioning that keeps you cool. Everything is connected in an intricate web of electrical circuits. An electrical circuit is made up of more than just one component. And how these components are connected together can make a big difference in how the system performs. In today's video, we will be exploring two types of circuits: series and parallel connections. In this section, we'll examine how voltage, current, and resistance are influenced in each type of circuit. To help you better grasp the electrical concept of series and parallel connections, we'll use the analogy of water flow in pipes with different connections to compare with the electrical circuits. Finally, we will take a closer look at the electrical components in our home circuit, and demonstrate how the devices we rely on every day are connected. If you enjoy the content, please don't forget to hit the like button, subscribe to the channel, and turn on the notification bell so you never miss any update. Before we dive into series and parallel connection, let's look at a simple circuit with 6 volts battery and one bulb at 12 ohms. Using Ohm's law, we can easily calculate the current to be 0.5 amps. In a series circuit, components are connected end-to-end in a single path. For example, if we add one more bulb in series, this means we are connecting the new bulb in the same path as existing bulb. And the total resistance is simply the sum of the individual resistances. R total equals to R1 plus R2. The total resistance will be 24 ohms. The current flow through each bulb is the same, in which I equals to I1 and equals to I2. But the higher total resistance means the current flow is reduced to around 0.25 amps. As a result, the bulbs appear dimmer. Additionally, the voltage across each bulb is reduced as well. If we apply Ohm's law, V equals IR, we can get each bulb has a 3 volts voltage across them. And the sum of the individual voltage, V total equals to V1 plus V2, will equal to total voltage of battery supply. Similarly, if we add extra one more bulb in series, the total resistance increases to 36 ohms, and current is reduced to 0.167 amps. The voltage across each bulb is further reduced to 2 volts. It is important to note that each time we add a new load component in series, the voltage across every load component in the same path decreases. This can affect the component's operation if the voltage level is reduced below the rated voltage. Also, any broken part in the series circuit can break the entire circuit, and all components along the same path will stop functioning. Let's turn our attention to parallel connections. In a parallel circuit, components are connected in a way that each of them has its own separate path to the power source. A parallel circuit can also be distinguished by examining the point where the conductors divide into separate paths, or we call that node. The voltage across each bulb is the same as the battery supply voltage, where V total equals to V1 and equals to V2. We can calculate the current flowing through each bulb to be 0.5 amp, similar to current flowing through the bulb in the original circuit, therefore the brightness of each bulb is not affected. However, in parallel circuit, the total current will be the sum of individual currents, I1 and I2, which will result in total current of 1 amp. We can also obtain the total resistance by using the formula 1 over R total equals to 1 over R1 plus 1 over R2, which the R total reduced to 6 ohms. Then, we can calculate the total current through the division of voltage by the total resistance, which will also result in a similar value of 1 amp. Similarly, if we add one more bulb in parallel, the total resistance will reduce to 4 ohms. The total current flow will increase to 1.5 amps, but the voltage across each bulb will remain the same. A parallel circuit can bring several advantages. Firstly, the voltage is maintained even though more components are added in parallel, and the operation of each component will not be affected. Additionally, if one of them is spoiled, the others connected in parallel can still function normally. So, that's a brief overview of how voltage, current, and resistance is affected in both series and parallel circuits. To better understand the concept of series and parallel connection, let's compare it to the analogy of water flowing through pipes. Imagine we have a water barrel connected through pipes and filter to a container on the floor. The water barrel at higher level has potential energy that allows water to flow, and the filter is filled with stone that can resist the water from flowing. The whole system is similar to a battery that has electrical potential difference or voltage, allowing current to flow through a circuit, with a bulb as the primary resistance. In case of a series connection, if we add another filter in the same path, more stone blocks the path, increasing the resistance to water flow, which results in a slower flow rate and takes more time to fill up the container. Similar to our explanation previously, adding another bulb in series increases the total resistance, reduces the total current flow, and causes the bulb to appear dimmer. On the other hand, in a parallel connection, if we add a filter in parallel, it provides another path for the water to flow, resulting in an increased flow rate at the main pipe, which is the sum of flow rate across each filter. The total resistance to water flow is said to be lower, and as a result, the container fills up faster. This is similar to adding another bulb in parallel, where the total resistance decreases, and the total current increases. So, that's the explanation of series and parallel connection. With a little practice, you'll be able to apply these principles to any circuit you come across. Now, let's talk about the application of series and parallel connections in our homes. In fact, most of the appliances we use in our homes are connected in parallel. But why is that? As we mentioned earlier, the parallel circuit has certain advantages, such as the operation of each device being independent of the others. For example, we can turn on or off any of the devices in our home individually, and if one device fails, the others can continue to function normally. Parallel connections also provide same voltage level to all connected devices, which is another reason why they are commonly used in our homes. For domestic purpose, most electrical appliances are manufactured to operate at the standard rated voltage, similar to the voltage level of all plugs in our homes. Since most devices in our home are connected in parallel, you may wonder where we can find series connections. Series connections are typically found between the switching components and the device itself. This allows us to easily connect or disconnect the device as needed by turning on or off the switches. Both series and parallel connections can also be found in the electronics part of devices. If you are aware of any other applications of series or parallel connections, feel free to share them in the comments section below. Thank you for watching today's video on series and parallel connections. I hope the explanation has helped you to understand the concepts better, and how they are applied in our daily lives. So, the next time you plug in your devices at home, you'll know they are connected in parallel to each other. Please like, subscribe and turn on the notification of our channel. We will constantly update more topic covering electrical knowledge in future.